On paper, the math promised we had beaten physics. By only activating a fraction of an AI model at any given millisecond, we were told we could run trillion-parameter intelligence for the price of a budget smartphone chip. But in the server rooms of 2026, a quiet crisis is unfolding. The math worked. The silicon did not. What was supposed to be the cheapest era of computing has instead run into a physical wall of copper, memory, and latency spikes. To understand why the industry is hitting this wall, we have to look at how we got here. For years, making AI smarter meant making it bigger. But running a traditional dense model is incredibly wasteful. Every time you ask a dense model to spell a simple word, every single parameter inside its massive network has to spin up and perform a calculation. It is the computational equivalent of waking up an entire university faculty just to answer a grade school question. Mixture of Experts, or MoE, was supposed to solve this. Instead of one massive, monolithic brain, an MoE model is split into smaller, specialized subnetworks called experts. A central router receives your prompt and decides which two experts are best suited for the task. The rest of the model stays dark. On paper, you get the intelligence of a massive model with the running costs of a tiny one. For a while, the marketing worked. Tech companies rushed to deploy these sparse models, claiming they had unlocked a free lunch. But then came the benchmarks. In late 2024 and throughout 2025, researchers began deploying standardized stress tests, culminating in the MoE-CAP benchmark. The results were a cold shower. CAP stands for cost, accuracy, and performance. What these rigorous evaluations revealed is that saving math operations, or flops, does not automatically translate to real-world performance. You can slash your mathematical calculations by 80%, but your physical hardware might actually run slower. The industry had optimized for the math on the whiteboard while completely ignoring the physical limits of the machines running it. To understand why, imagine a world-class restaurant kitchen with 16 highly specialized chefs. One only cooks fish, one only bakes pastries, one only chops onions, and so on. But the kitchen has a fatal design flaw. There is only physical counter space for two chefs to work at any given moment. Every time a customer orders a salmon fillet followed by a chocolate cake, the kitchen manager has to physically drag the onion chopper off the counter, run to the break room, wake up the pastry chef, and pull them to the line. If the orders come in randomly, the kitchen grinds to a halt. The chefs are not slow. The food is not bad. The kitchen fails because the chefs spend all their time packing up their tools and swapping places. This is the exact bottleneck happening inside modern GPU clusters. This swapping process is what engineers call the VRAM tax. Even though an MoE model only uses 2 experts at any given millisecond, all 16 experts must live in memory. If they do not, the system has to fetch them. This is where local consumer hardware completely breaks down. A technical paper released in February 2026, introducing a framework called DALI, detailed exactly why your local PC stutters when running these models. Because consumer devices do not have enough ultra-fast video memory to hold all the experts at once, the system is forced to constantly offload them to system RAM or even slower solid-state drives. When your prompt shifts from writing Python code to writing creative fiction, the router suddenly demands different experts. The system must copy gigabytes of weight data over the narrow PCIe lanes of your motherboard. The processor sits idle, waiting for the data to arrive. The result is a sudden, jarring pause in your chat window. The industry is growing desperate for a solution. In June 2026, researchers introduced a technique called FlexMoE, which attempts to prune the unused, dusty corners of these experts so they can fit into smaller memory slots. But this software band-aid highlights a deeper problem. When you start shrinking the experts to save memory, you risk what researchers call expert collapse. A study from May 2026 investigated how sparse routing works in complex visual tasks. They found that for these models to actually maintain their accuracy, they must route tasks to multiple experts simultaneously. If you try to save hardware costs by restricting the routing or pruning the experts too aggressively, the model's reasoning abilities collapse. We are caught in a physical vice. Make the model smaller to save memory, and it gets dumber. Make it smarter, and your hardware chokes. This explains a massive mystery in the AI industry. Why the exact same AI model can feel lightning fast 1 minute and painfully slow the next. For cloud providers, sparse MoE models are an economic miracle during quiet hours. They allow them to pack more users onto fewer chips, slashing their operational costs. But during peak traffic, when thousands of users are asking completely different questions at the same time, the system breaks. Because the requests are so diverse, the router is forced to call upon every single expert at once. The GPUs must constantly synchronize with each other, pausing their calculations to share data over the data center network. The hardware bills mount, the latency spikes, and the cloud providers are forced to quietly throttle your speeds or hide the delays behind animated typing indicators. The golden era of pure software scaling has run its course. For years, we operated under the assumption that any computational bottleneck could be solved with a clever new architecture or a slightly different mathematical formula. But as we push deeper into 2026, we are learning a hard lesson. You can design the most elegant, sparse neural network on a whiteboard, but it still has to run on copper, silicon, and electricity. Until our hardware architectures evolve to support dynamic, physical memory routing at the hardware level, the promise of cheap, limitless artificial intelligence will remain a theoretical dream, taxed heavily by the cold, hard realities of physics.